Aha! Awesome. All right, so we're looking at the 6-4 notes. We are going to be dealing with the graphs and inverses. We're dealing with graphs and inverses. Again, yeah. Good news, though, we're all really familiar with transformations at this point. So, Maddox,
Yeah.
what does A do to a graph? Oh, sorry, my bad. What does the A value do to a graph? Yeah, it's a big R. Big R. That's what we did in 6-1. Maybe 6-2. Yeah, what does A do? All right, it's a multiplier. So if you multiply me by a number bigger than 1, am I going to get bigger or smaller? Bigger. So I would stretch out, right? If you multiply me by a number smaller than 1, would I get bigger or smaller? Smaller. I would get compressed into something smaller. And if A was negative, you would take a positive value and then turn it into a negative value, so it would reflect over the x-axis. All right, redemption round. What does H do?
Does it divide?
Does not. What is it touching? What's happening with H? What is it impact? What's the immediate impact of H?
Going off of it.
X, yeah. X is horizontal, right? And if I had an x value of 2, and I subtracted 5 from it, then all of a sudden it would be way over here at -3, right? So what happens if I go from 2 to -3? What are we doing?
You're going to the left.
Yeah. It's a shift, right? Yeah. And what does K do?
K.
That's your up and down transformation. That's exactly right. When we hop from exponential to logarithmic, though, logarithmic.
I learned how to do some of those problems.
Yeah, that's right. Yeah, good. You're treating this week properly. We would look at that. F of x equals a times log base r of x minus h, and all of that plus k. A does the same thing. It's going to stretch, compress, or reflect. H is your horizontal transformation, and K, that's your vertical transformation. All right. So we've studied A, H, and K a bunch in this class with parabolas, absolute value, square roots, cube roots. We've done it all. Now we're dealing with exponential and logarithmic. Hint, they are inverses of each other. So if I look at the parent y equals 2 to the x power, just a quick graph, nothing too fancy. There we have an x-axis, here we have a y-axis. Alright, what's 2 to the 0 power? Easy. What's 2 raised to the 0 power? 1. So we get the coordinate point 0, 1. Now, to the left, as Beyonce asks us to do, we get closer and closer to the x-axis. To the right, we blow up super fast. Okay? Now, the inverse. The inverse
it would be the opposite.
to an extent.
Wouldn't it be -1 then?
What do we know about functions and their inverses
Switch.
on the the x and the y value switches? Okay, good.
So then,
Yeah, let's do a couple of these. If my x value here is 2, what's the y value? What's 2 to the 2? 4. So this is the coordinate point 2, 4. Great. What about over here? If my x value is -1, what's my y value? 1/2. Good job, Marissa. Yeah, that's right, big dog. Proud of you there. So 2 raised to the negative first power becomes 1/2. Boop. What about way over here? What if we had a -4 for my x value? What is the y value going to be? Let's go. Yes. 1/16. Good job. All right. So what does an inverse do? Danica said it switches the x and the y. So let's look at this y-intercept of 0, 1. What will that become for the log function y equals log base 2 of x? 1, 0. So x and y switch. All right, they're going to switch places. So I get the coordinate point 1, 0. 1, 0 is right there. What about the coordinate point 2, 4? What will that correspond to over here? Say it again. Did I say that right? I said it backwards, didn't I? It's fine. So the x value is 2, the y value is 4. That switches to become an x value of 4 and a y value of 2. -1 and 1/2. What coordinate point does that go to?
1/2 and -1.
Yeah, so 1/2 on the x-axis and -1 on the y-axis. I see you, girl. You can't hide from me. What about -4 and 1/16?
Like negative.
Yeah, so not a half of a half, a half and a half and a half. Goes all the way down here to 1/16, comma, -4. And so the graph will look like this. What symmetry do graphs of functions and their inverses have? What is that type of symmetry called? Go ahead, Emmett. I know you know. What?
I do not.
You don't know.
Can you repeat the question?
What type of symmetry does the graph of y equals 2 to the x and y equals log base 2 to the x, or 2 of x, excuse me.
Oh, why equal that?
What about it? What's the transformation? What transformation of y equals x do I do with this graph to get to this graph? Yeah, you take the corner and fold it over. That's, I agree with you, and absolutely, that's not the name of the transformation.
Yeah, I remember when we did this. Yeah.
So we have the line y equals x. All right, you take one graph, becomes this graph, right? What is that transformation called? A reflection. Yeah, reflection. If I take this graph and reflect it over the line y equals x, then it gives me this here, correct? Which is the graph of the log function. So, exponents and logarithms are inverses of each other. Now, Danica, what's the big idea with inverses? What's that big word that we wrote on the front of that page that one time? Switch. Yes, good.
The y and the x, or the x and the y.
Yeah, that's right.
My bad.
What is the domain of the exponential function?
Negative infinity to
Negative infinity to infinity. Yeah, good job. Domain is left to right, range bottom up. So what is the range here?
infinity.
0 to infinity. Yeah, we start at 0, we go all the way up to infinity. Good. What was our asymptote for this guy? What's the equation of the asymptote?
Y equals
0.
0.
Yeah, good. The line y equals 0. This graph will never touch 0. So my asymptote y equals 0.
Mr. Stephen,
Sub dog.
isn't 0 included?
It is not included. We will never touch 0, so it's not included. But every number bigger than 0 will get included. Yeah.
Okay.
All right. So let's go over here. Hey, Maddox. Danica is absolutely correct. When we talk about inverses, it switches our x's and our y's. It's going to switch x and y's.
X equals
Okay, good. The asymptote now. X equals 0. Good job. What will the domain be?
Would it be infinity? Wait, would it be negative infinity?
It would not. No, what we're switching x and y's. Domain describes your x values. Range describes the y values. So if I switch that around,
0.
the domain is going to be 0 to infinity. The range then will become
Negative infinity.
2.
Infinity.
Good job. That's it. That's exactly right. Good job. Really, really, really good job.
Dang it.
All right. So let's do a couple practice problems then. And I'm going to put this just slightly off center because there's one kid with that perfectionist thing. They're going to look at that, right? On this video, they're going to look at that and they're going to go, oh, why did he do it that way? And I'm going to go, haha. Oh, you know what? Let's make it even worse. Let's make it worse. All right, so we're going to do a couple examples here. Describe the transformations
Thank you.
then determine, yeah, bless you, sorry, the domain, range, and
Describe the.
if it's a growth or decay. All right. So, example 1. Let's go. Y equals 2 times the log base 2 of x minus 3. So we need to know, what are the transformations? What's the domain? What's the range? Is this a growth or a decay?
Come on, bring it back over here.
And do we have or what is the equation of the asymptote? What do you need? Nope. Brawl Stars? Love it. All right. Trin, how many transformations do we have here? 2. Really good job. Name one of those transformations. Really good job. Really good job. How you confuzzled, big dog? Listen, do you remember how many times we've had an A value?
I forgot what I was writing down.
A value of 2. My 2 here is a stretch by 2. Good job, Trin. Kimmy, can you tell me the other transformation? Yes.
Going up
Easy. Is that an H or a K?
or
Yeah, so it wouldn't be up or down. To the right by 3. Yep, good job. Good job. So right 3 units. Okay. So thinking about our parent function, the parent function is the log. Is that going to impact the domain or the range when we shift to the right 3 units? Yeah. So if I shift this graph right here, if I shift it to the right 3 units, that's going to impact the domain. Right? If I shift that whole graph to the right 3 units, boop, there. That's going to impact our domain. Marissa, what is the domain going to be now? Good job. We're going to start at 3 now, and we're going to go all the way to infinity.
Three's included.
It is not included. It's an asymptote you cannot touch. Elvis, hit me. What's the range on this, big dog? Take this graph right here, shift it to the right. Yeah, what up, big?
How is
that one 0 to infinity if it's on the 1, but this is 3 to infinity?
It's because it doesn't reach 0. It gets infinite and goes to it. It's because there's no like H or K to shift it.
Are there x values between 0 and 1 here?
Yeah.
Yeah. We looked at an x value of 1/16, right?
Okay.
So we can't ignore the bottom half of this graph, right? So what I'm looking at here, we get close to 0, but we won't touch it. So it starts at 0. We got to include everything between 0 and 1, and then everybody after 1 as well. Did that answer your question? Was that remotely helpful? Let's go back to your question. What was your question?
So on that one, it shifted 1 to the right.
Say a little bit louder now.
That one is shifted 1 to the right.
No, this is the parent.
equation is 2 to the x.
No, this is the parent.
2 to 0.
There's been no transformations with this guy.
Oh, okay, I get it now. Because it gets confused in the thing.
Yeah, this guy. Yes. Number 1, that big guy takes the original and shifts it 3 to the right. Yeah. SpongeBob pants okay. I had to. I am so sorry. I'm so sorry. All right. Elvis, what was the range? Yeah, really good job. Really good job. Marissa, is this a growth or a decay? As we look at that graph from left to right, is it getting bigger and bigger and bigger, smaller, smaller, smaller? Bigger, so that means it is a growth. Really good job. Kimmy, can you tell me the equation of the asymptote?
Y equals, or no, x equals 2.
Yeah! Yes! 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 Let's go! Great job. Good job, chat. Proud of you on that. All right, let's try another one. Let's try y equals log base 1/2 of x, and we're gonna go minus 4.
Oh, this is fun.
I don't even know. I don't even know. I don't even know. So let's take a look. Does R, the value of R, does that create a transformation of the graph? No. It tells us a little bit of information. So that R value is not a transformation. Elvis, what is the transformations here? What does that do to the graph? Really good. So we got to shift down 4 units. That's the only transformation with that graph. Domain. Yes, Kimmy? Yeah. Absolutely. Absolutely. We're going left to right.
Negative 4 to infinity.
Well, let's take a look here. Let's take a look here. If what was that? Did something fall somewhere? Oh, it's back behind the refrigerator. Sounds great. If Danica, domain, we're reading left to right. Left to right. So if, Danica, I shift this down 4 units, does that change my domain?
No.
No, not at all. An up and down transformation is not going to change the domain in any way, shape, or form. So what is our domain? Zero to infinity. It starts at 0 and it goes off to the right forever. Forever. So 0 to infinity. The range. Emmett, what do you got on that?
Negative infinity.
Really good. Ugh. And they were roommates. All right, so growth or decay?
Decay.
How do you know?
Because it's shifting down for you.
No, if I take a graph that is growing and I shift it down, it's still growing.
Oh.
From left to right. From left to right, is this graph getting bigger or smaller? Yeah, let's do a quick exploration here. If I have y equals log base 1/2 of x. Connor Cooley, brother, rewrite this in exponential form.
That would be 1/2.
Your exponent is always whatever the logarithm is equal. A logarithm is an exponent.
Yeah, no. But R, okay, so
1/2 to what power?
10.
I don't have a 10 in any of this.
Y.
To the y. And what does it equal? X. Alright, so this function is this equation. These are the same thing. That's the definition of logarithms. We need to be able to go from exponential to logarithmic form and logarithmic back to exponential form. So looking at this, we have an x value and a y value. What would be easier to determine? If I plug in values for x or if I plug in values for y? Which would be, yeah. So let's let our y values go from -2, -1, 0, 1, and 2, and then we'll be able to determine the shape of this graph. So let's start with 0. Anything raised to the 0 power equals 1. Beautiful. Beautiful. So what's 1/2 raised to the first power? 1/2. What's 1/2 raised to the second power? 1/4. So now let's go back. What does 1/2 raised to the negative first power equal? Alright, so 1/2 raised to the negative first. That is, yeah, that's exactly right. So 1 raised to the negative first and 2 to the negative first. So a negative exponent goes to the other side of a fraction, becomes positive. So that 1 will now go down here, and the exponent becomes a positive 1. The 2 goes to the top, and now I have a positive exponent. And 2 to the first divided by 1 to the first is just 2. Notice that the negative exponent did not change the sign for that output. This is just a 2. So with that in mind, Trin, what is 1/2 raised to the negative 2 power? That's 1/2 to the first. All right. So the negative second power. That negative exponent. Look what happened to that fraction when I switched the exponent from negative to positive. Do you see that? So that becomes 2 over 1 raised to the positive 2. So what's 2 squared? 4. Yeah, good. Good. So we get a 4 right there. So what will that look like on a graph? My x value of 4 has a y value of negative 2. My x value of 2 has a y value of negative 1. My x value of 1 has a y value of 0. My x value of 1/2 has a y value of 1. And my x value of 1/4 has a y value of 2. What's happened to the shape of this graph? What do y'all notice? Huh? It's a decay. So if r is betwixt 0 and 1, then what can we say about this graph? Is it going to grow or decay?
No, decay.
That is a decay. And if I have an r value greater than 1, what do we have? That's right. That right there, muy importante. And that is Spanish for somewhat important. So, let's get back to that problem. What is my r value on number 2? What is the r value there? 1/2. Do we have a growth or a decay? That's right. And our asymptote. What does x equal? 0. Good. The asymptote did not change. It only changes if we shift left and right. That asymptote of x equals 0 will only change when we shift left and right. Really good job. Really, really good job. Did anybody see what the homework was for 6-4 yet? Your teacher didn't post it? Biscuits. No, I gotta post it. Alright, so finding the inverse function. Steps to finding an inverse function do not change now that we're dealing with exponential and logarithmic functions. The process exact same. So we say that f of x is the same thing as y, step 1. Step 2, we say that y is the same thing as x, and this is where we switch. Step 3, we're going to solve. Solver. Solve for y. And step 4, we're going to replace y with f inverse of x. Alright, those exact same steps that we dealt with in regular function land, we're dealing with here. So, we got some work to do. Alright, so find the inverse. First example, we're going to go with that last problem. Y equals log base 1/2 of x minus 4. Alright, so we're in terms of y equals. What am I going to do next? Switch the x and the y. Good. So now we have x equals log base 1/2 of y minus 4. Now we got to go solve for y. How are we going to solve this for y? What's the first thing we're going to do? Add 4. We want to isolate that logarithm. Yeah, that's what we learned yesterday. So I get x plus 4 equals log base 1/2 of y. After we isolate, what do? Solving a logarithmic equation. These are in your notes from yesterday. Logarithmic equation. How do I solve a logarithmic equation? Convert it. and the base stays the same. So, convert this equation into exponential form. What do we get?
1/2 to x plus 4 equals y.
Oh, let's go. Is y by itself?
Yeah.
Yeah, now y is by itself. Great job. So I can replace the y with f inverse of x, and it becomes 1/2 raised to the x plus 4 power. Great job. Really, really good job. All right, we'll do one more example, and the rest of the day is yours to start in on all the homework. 26 problems yesterday. Did anybody finish? Yeah. Trin, how long did it take you?
I don't know.
Like 15 minutes?
I don't know. I was doing stuff along with it.
Yeah.
I burned myself twice while doing homework.
You burned yourself while doing homework.
I was cooking.
Okay, so you were cooking and homework at the same time? That's peak efficiency, dog. That is peak efficiency. Wait, what did you make for dinner?
I made cake and sausage.
Cake and sausage. For dinner?
No,
Oh.
dessert and dinner.
Oh, dinner and dessert. But you just had like plain sausage casing, like a just sausage.
I just had like a breakfast sausage.
Yeah.
Didn't have cake.
So you just had a bowl of breakfast sausage. I love you, pal. That sounds amazing. I wish my son would eat just straight up protein. That'd be great. He eats carbohydrates and dairy. So, grilled cheese sandwich.
Oh,
I love grilled cheese sandwiches. Pizza is carbohydrates and dairy. Chicken nuggets, no dairy. Fries, no dairy there.
Mac and cheese.
Mac and cheese, for sure. Yeah, that's exactly what my son will eat. He's got that one type of autism that'll only allow him to eat 3 things.
He's got great.
I heard a guy one time, when he was raising his kid, he goes, yeah, my son only eats foods in the shape of dinosaurs. And I thought, that's hilarious. Thank goodness my son eats his vegetables. This is when he was an infant and couldn't make choices. And now that he can make choices, he really generally only eats things in the shape of dinosaurs. It's awful. Have you seen dinosaur mac and cheese?
Yeah.
Yeah, they have like
So
Sonic
my
mac and
baby
cheese and all that.
cousin.
Yeah.
He loves dinosaurs.
Yeah. Well, he doesn't care about dinosaurs. He cares about his food being in the shape of dinosaurs.
We can't get him to eat anything else but dinosaur chicken nuggets.
Yeah.
That's all he eats.
Dinosaurs are protein. Alright. Let's find this one. Let's go 4 raised to the x plus 7. Alright, let's find the inverse. What form did we start in? What type of function is this? Yeah, where's the variable? Yeah, this is exponential. Alright, so we start by y equals 3 times 4 to, to the x plus 7. And now the meaning of inverse, what do? Switch. So x equals 3 times 4 to the y plus 7. Now we gotta do a little work.
Exactly.
Why are you afraid of work, dog? That's the American dream, is to have the freedom to work.
My brain hurts.
And you turn the American dream into the American sleep.
Yeah. I love sleep.
Alright, talk me through it. What's our first step? To go solve for y. Minus 7.
Oh.
So x minus 7 equals 3 times 4 to the y. What's our next step?
Divide by 3.
Yeah, you will. Good. So we have x minus 7 all on 3 equals 4 to the y power. Oh, great. Great. We got the base with the exponent isolated. What's our next step?
Divide by 4? No. Y equals 4 to x minus 7.
So we're going to convert it to what form? Yeah, currently we're in exponential. We got to switch it to logarithmic. That's right. When you convert, Elvis, you said it earlier. When we convert, what do you want to remember in the process of converting?
The base stays the same.
The base stays the same. So what is our base here?
4.
I'm going to leave it on the right-hand side because I'm lazy. What is the exponent now going to be? X minus 7 over 3. Make sure that you're writing it as an exponent and not writing it as a multiplier, because that's confusing, and all of that equals y. Alright, so y, oh, so no, not y. Last step, notation, a little bit of housekeeping here. F inverse of x equals 4 raised to the x minus 7 over 3 power. And that is our inverse. It's going to be enough to get you going on the 6-4 homework.